sklearnconfigcontext. Description: the config context in scikit-learn sklearn is a powerful tool for managing and customizing the configuration of your machine learning pipeline. It provides a structured way to set and modify various aspects of your model building process, ensuring consistency and reproducibility. Inputs. Data: the input data, usually in the form of a pandas data frame or NumPy array, containing features and target variables. Model parameters: the hyperparameters of the chosen machine learning model, such as the number of estimators in a random forest or the regularization strength in a linear regression. Preprocessing options: the methods to be used for data preprocessing, such as feature scaling, imputation of missing values, and encoding categorical variables. Evaluation metrics: the criteria used to evaluate the performance of the model, such as accuracy, precision, recall, or F1 score. Outputs. Trained model: the fitted machine learning model, ready for making predictions on new data. Performance metrics: the evaluated scores of the model based on the chosen metrics. Model insights: information about the model's learned patterns and relationships, potentially including feature importance or coefficient values. Steps. Data preparation: this involves cleaning, transforming, and engineering features in the data. Model selection: choosing the appropriate machine learning model based on the problem and data. Characteristics. Model training: fitting the model to the prepared data, learning patterns and relationships from the input features. Model evaluation: assessing the model's performance using various metrics on a separate evaluation dataset or using cross-validation. Model tuning: optional, optimizing the model's hyperparameters to improve its performance using techniques like grid search CV or randomized search CV. Metrics. Accuracy: the percentage of correctly classified instances. Precision: the ratio of correctly predicted positive instances to the total number of instances predicted as positive. Recall: the ratio of correctly predicted positive instances to the total number of actual positive instances. F1 score: a harmonic mean of precision and recall, providing a balanced measure of performance. Mean squared error MSE: the average of squared differences between actual and predicted values, commonly used for regression problems. Root mean squared error RMSE: the square root of MSE, providing a more interpretable measure of error. Visualization plots. Confusion matrix: a visual representation of the model's classification performance, showing true positives, true negatives, false positives, and false negatives. ROC curve: a graphical representation of the trade-off between true positive rate sensitivity and false positive rate 1 specificity for different classification thresholds. Precision recall curve: a plot showing the relationship between precision and recall for different thresholds. Feature importance plot: a visualization that shows the relative importance of features in the model's decision-making process. Residual plot: a plot of the difference between predicted and actual values, used to assess model assumptions and identify potential issues. Fine-tune parameters. Regularization strength: for linear models, controlling the complexity of the model and preventing overfitting. Number of estimators: for ensemble models like random forest, determining the number of trees or base models used in the ensemble. Maximum depth: for decision tree-based models, limiting the depth of individual trees to control complexity. Learning rate: for gradient-based models, determining the step size used in the optimization process. Uncertainty methods. Confidence intervals: estimating the range of plausible values for the model's predictions based on the uncertainty in the training data. Bayesian methods incorporating prior knowledge and uncertainty into the model's estimation process. Ensemble methods using multiple models to make predictions and aggregating their results. Reducing the impact of individual model errors. Challenges and fixes. Challenge 1: overfitting when the model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: a complex model with many features and a small training dataset may lead to overfitting. Fixes to challenge 1. Use regularization techniques like L1 or L2 to penalize complex models. Simplify the model by reducing the number of features or using a simpler model structure. Increase the size of the training dataset. Challenge 2: underfitting when the model is too simple to capture the underlying patterns in the data. Sample use case that resulted in challenge 2: a linear model may underfit a dataset with nonlinear relationships between features and the target variable. Fixes to challenge 2: use a more complex model structure, such as a nonlinear model like a decision tree or neural network. Add more features to the dataset that capture the complex relationships. Consider feature engineering to create more informative features. Challenge 3: data imbalance when the target variable has a skewed distribution, leading to biased predictions. Sample use case that resulted in challenge 3: in a fraud detection dataset. The number of fraudulent transactions is significantly lower than legitimate transactions. Fixes to challenge 3: use resampling techniques like oversampling or undersampling to balance the classes. Employ cost-sensitive learning, where misclassification costs are adjusted based on the class distribution. Use appropriate evaluation metrics that account for data imbalance, such as precision recall curve or F1 score. Challenge 4: missing values. The presence of missing data can affect the model's performance. Sample use case that resulted in challenge 4: missing values in certain features of a medical dataset might make it difficult to train a reliable model. Fixes to challenge 4: use imputation techniques to fill in missing values based on other features or the distribution of the variable. Remove features with too many missing values. Consider using models that are robust to missing data, such as tree-based models. Challenge 5: categorical features. Handling categorical variables non-numerical is crucial for model training. Sample use case that resulted in challenge 5: a dataset with features like gender, location, or product type needs to be encoded before training. Fixes to challenge 5: use one-hot encoding to create binary features for each unique category. Use ordinal encoding if the categories have a natural order. Consider using models that can handle categorical variables directly, such as decision trees or ensemble models. Challenge 6: high dimensionality when the number of features is very large. It can lead to overfitting and computational inefficiency. Sample use case that resulted in challenge 6: a dataset with thousands of features may require dimensionality reduction techniques. Fixes to challenge 6: use feature selection methods to choose the most relevant features. Use dimensionality reduction techniques like principal component analysis (PCA) or TSNE to reduce the number of features. Challenge 7: scalability. Training models with large datasets can be computationally intensive. Sample use case that resulted in challenge 7: a very large image dataset requires efficient algorithms and resources for training. Fixes to challenge 7: use efficient algorithms and data structures. Employ distributed computing techniques like Spark or Hadoop to distribute the computation across multiple machines. Consider using online learning algorithms that can learn incrementally from data.